White phosphorus is a soft, waxy, and translucent solid. It is insoluble in water, but soluble in carbon tetrachloride or carbon disulfide. It dissolves in boiling caustic soda in an inert atmosphere to give phosphine and sodium hypophosphite. It is highly toxic and extremely reactive. It exists as tetrahedral P4 molecules. These molecules are held together by weak van der Waals forces of attraction. Hence, it has a very low melting point of 44 degrees Celsius. As you can see from the structure, each phosphorus atom is covalently bonded to 3 other atoms of phosphorus. The bond angle in a P4 molecule is 60 degrees, which is much less than the expected or theoretical bond angle. You know that when pure p orbitals overlap, the theoretical bond angle expected is 90 degrees. This angular strain in the molecule makes white phosphorus unstable and therefore highly reactive. Therefore, white phosphorus ignites spontaneously in air at about 35 degrees Celsius. That is, at a temperature slightly higher than room temperature, to form phosphorus pentoxide. The equation for this reaction is shown here. This angular strain in the molecule makes white phosphorus unstable and therefore highly reactive. Therefore, white phosphorus ignites spontaneously in air at about 35 degrees Celsius. That is, at a temperature slightly higher than room temperature, to form phosphorus pentoxide. The equation for this reaction is shown here. Owing to its high reactivity, white phosphorus is stored underwater. White phosphorus glows in the dark. Do you know why? In contact with humid air, white phosphorus gets oxidized. This reaction is associated with the emission of light. As a consequence, it glows in the dark. Note that the emission of light or electromagnetic radiation during a chemical reaction is called chemiluminescence. Thus, white phosphorus exhibits chemiluminescence. When white phosphorus is heated to about 250 degrees Celsius in the presence of sunlight, a stable allotrope of phosphorus is obtained, which is called red phosphorus. Red phosphorus is an iron-grey, lustrous crystalline solid that is odorless, non-toxic and insoluble in water as well as in carbon tetrachloride. It doesn't dissolve in boiling caustic soda, but dissolves in alcoholic potash. It exists as a polymeric solid. It means that red phosphorus consists of a chain of P4 units that are linked together by single covalent bonds. Hence, it is stable under normal conditions and doesn't ignite in air. It is therefore not stored in water. It undergoes combustion only when heated to about 400 degrees Celsius. Note that red phosphorus doesn't exhibit chemiluminescence. The other principal allotrope and thermally the most stable is black phosphorus. It is a highly polymerized form of phosphorus. It has a layered structure. It exists in two forms, namely alpha black phosphorus and beta black phosphorus. When white phosphorus is heated at 473 Kelvin, under high pressure, it forms beta black phosphorus. It doesn't ignite in air up to 673 Kelvin. On the other hand, when red phosphorus is heated to 803 Kelvin in a sealed tube for a sufficiently long time, it forms alpha black phosphorus. Alpha black phosphorus has opaque monoclinic or rhombohedral crystals, while beta black phosphorus consists of corrugated sheets that result in the formation of flaky layered crystals. Alpha black phosphorus doesn't conduct electricity, but beta black phosphorus does. You know that phosphine is a hydride of phosphorus. It was discovered by Jean Gemry in 1783. It is formed in the soil by the bacterial reduction of phosphates. Let us begin our study with the methods to prepare phosphine. Phosphine can be obtained by the hydrolysis of metallic phosphides with water or dilute mineral acids like hydrochloric acid or sulfuric acid. Calcium phosphide or sodium phosphide, on being hydrolyzed with water, produce phosphine. Similarly, when aluminium phosphide is hydrolyzed with hydrochloric acid, it gives phosphine. The equations for these reactions are shown here. Phosphine is also prepared by hydrolyzing white phosphorus with a concentrated solution of sodium hydroxide. This is the laboratory method to prepare phosphine. Let us take a quick look at it. A concentrated solution of sodium hydroxide and white phosphorus is taken in a round-bottomed flask, as shown in the apparatus arranged here. The reaction is allowed to take place in an inert atmosphere of carbon dioxide or oil gas, because phosphorus would otherwise react with oxygen and lead to an explosion. The contents of the round-bottom flask are heated to produce phosphine gas. This gas is delivered into a trough of water. Bubbles of the gas catch fire as soon as they come in contact with air to form rings of smoke, called vortex rings, as shown here. This indicates the presence of highly inflammable phosphorus dihydride or diphosphine as an impurity in phosphine. Are you aware of this fact? The flickering light in marshy places is believed to be corpse candles or ghostly lights. However, in fact, the origin of the flickering light, called will-o'-the-wisp, is due to the spontaneous inflammation of diphosphine present in marshes. The phosphine obtained in the process is purified by absorbing it in anhydrous hydrogen iodide that forms phosphonium iodide. This, on heating with potassium hydroxide, evolves phosphine gas that does not have diphosphine. Pure phosphine can also be obtained by using alcoholic potassium hydroxide instead of an aqueous sodium hydroxide solution. This is because diphosphine is insoluble in alcohol. Diphosphine can also be removed by passing the gas through a freezing mixture in which diphosphine condenses while phosphine doesn't. Activated charcoal or phosphorus pentoxide can be used to absorb the liquid hydride diphosphine from phosphine gas. Next, let us see how phosphine differs from ammonia as far as bond angle is concerned. You already know that ammonia has pyramidal geometry with a bond angle of 107.8 degrees. Similarly, phosphine is also expected to have pyramidal geometry with nearly the same or similar bond angle. However, the bond angle in phosphine is only 93.5 degrees. How do you account for this? Try to explain this variation by comparing the electronegativities of the central atoms in their respective hydrides. You know that phosphorus has less electronegativity than nitrogen. As a consequence, the electron density around the central atom, phosphorus, is less concentrated as compared to nitrogen in ammonia. In other words, the bond pair of electrons is much farther away from the central atom in phosphine than it is in ammonia. As a result, the lone pair causes even greater distortion in phosphine. Thus, the bond angle in phosphine decreases to 93.5 degrees. Moreover, the bond angle of 93.5 degrees suggests that the orbitals used for bonding are close to pure p orbitals. Let us first study the properties of phosphine. Phosphine is a colorless and extremely poisonous gas that smells like garlic or rotten fish. Unlike ammonia, it is slightly soluble in water, and the aqueous solution is neutral. It is more soluble in carbon disulfide and other organic solvents. The melting and boiling points of phosphine are much less than that of ammonia due to the absence of hydrogen bonding. It condenses to a colorless liquid at -87 degrees Celsius and freezes at -132 degrees Celsius. Phosphine acts as a Lewis base analogous to ammonia due to the presence of a lone pair of electrons. However, it is a weaker base than ammonia because its central atom, phosphorus, is larger in size and less electronegative. Its basic character is evident from its reactivity towards anhydrous halogen acids such as anhydrous hydrogen iodide. Phosphine combines with hydrogen iodide, thereby acting as a Lewis base by donating its lone pair to form phosphonium iodide salt. Talking about phosphonium salts, the phosphonium ion has a structure similar to the ammonium ion as shown here. Do you know why the bond angle of phosphonium ion is higher than that of phosphine? Try to answer this question on your own before looking at the answer. The central phosphorus atom is tetravalent in phosphonium ion and trivalent in phosphine. This indicates that there are 1 lone pair and 3 bond pairs in phosphine. While all the 4 are bond pairs in phosphonium ion, you know that the magnitude of repulsion between a lone pair and a bond pair is greater than between 2 bond pairs. Hence, the extent of repulsive interaction in phosphonium is less than in phosphine. As a result, the bond angle in phosphonium ion is greater than in phosphine. Pure phosphine is non-combustible at normal conditions, but catches fire when heated to about 150 degrees Celsius to form phosphoric acid. When phosphine is heated to about 440 degrees Celsius in an inert atmosphere, or when it is subjected to an electric spark, it decomposes into its constituents, namely red phosphorus and hydrogen. Also, an aqueous solution of phosphine decomposes in the presence of light into red phosphorus and hydrogen. It burns with an explosion when it comes in contact with even the smallest amounts of oxidizing agents such as nitric acid and chlorine gas. Nitric acid oxidizes phosphine to phosphorus pentoxide and itself gets reduced to nitrogen dioxide as shown in the equation here. Similarly, the equation corresponding to the oxidation of phosphine in the presence of chlorine is also shown. When passed through aqueous metallic salt solutions such as copper sulfate, silver nitrate and mercuric chloride, phosphine gas precipitates the corresponding metal phosphides. As can be seen from these equations, copper phosphide is precipitated from copper sulfate, silver phosphide from silver nitrate, and mercuric phosphide from mercuric chloride. You know that the reducing power of the hydrides of group 15 elements gradually increases on descending the group. Hence, the reducing power of phosphine is greater than its analog ammonia. It reduces auric chloride to metallic gold as shown in the equation here. Let us now turn to the uses of phosphine. The hydrolysis of calcium phosphide finds use in the manufacture of Holmes signals. A mixture of calcium phosphide and calcium carbide is taken in a container and sealed. When needed, the container is pierced and thrown into the sea. As water enters the container, it reacts with the mixture and produces brilliant flashes of light, a bright luminous flame which serves as a signal to approaching ships. The bright luminous flame is due to the formation of phosphine and acetylene on the hydrolysis of calcium phosphide and calcium carbide. Note that the spontaneous flammability of phosphine is due to the presence of diphosphine. The same reaction is also used in smoke screens. The phosphine obtained catches fire and produces the required smoke.